All right, so today we're going to take a look at uh, gradients and especially in back propagation. Uh, and this is basically the most important part of deep learning. It is, although the basic, uh, but it is very important to understand gradients and how gradient flow works. Um, and when you take a look at the modern deep learning architecture, the focus is to not focus on the data output of a neural network, but on the other hand, you focus on the gradient flow itself. So by looking at the gradients and how the overall gradient distribution looks like, we can successfully gauge the amount of learning that the model would do, and also the amount of overfitting that the model would do, and even about the amount of generalization that the model would do um, while before we even train the neural network model. And I think this is a relatively new type of standpoint when it comes to like, oh, focus on the gradient flow more on what the data is, what the result of the data is, and modern state-of-the-art deep learning models. It makes more sense to understand those state-of-the-art deep learning models in the perspective of gradients than the actual data that it is processing. Now, to give a little bit more meat and context into what I'm saying, I'm going to discuss about what we call as the forward pass and the backward pass. And the terminology itself seems to be a lot fancy and formal, but in reality, it's not the case at all. Simply stating, the backward pass is back propagation. So it's in terms of the gradients. We're focused more on the gradients. And for the forward pass, it's basically forward propagation, where we are uh, computing from the input to the output, and we're basically forward passing layer by layer into this deep neural network. That's called the forward pass. And let me just draw it now. So let's say that we have multiple models right here, and we have a data right here, and we have an output. Now the forward pass discusses about how does the input transform itself into the output, while the backpropagation focuses on how the error or the output, or how the error rates of the output gets updated in respect to all of these parameters in the neural network model and up to the input. So again, we can just write this as the backward pass and the forward pass. And this is basically the, I think, a simple name for backpropagation. And this is forward pass is simply the forward propagation. Okay, sorry, got a little distracted there. Okay, so now this is what we're going to focus on, the backward pass and the forward pass. Now in the in-depth section of the video, we're going to get a general overview of basically what is backpropagation and how does it work. But basically, it uses gradients, it uses derivatives, partial derivatives of the error with respect to a specific parameter or a weight scheme. And using this derivative, we just simply update the neural network model, and that's how it optimizes. That's how neural networks optimize. And you know what? Let me just go into this. All right, I think it's not that big of a deal. I think in the advanced or the in-depth section of the video that I could record, I would be going into like the nitty-gritty details of exactly how backpropagation works. But it simply involves chain rule and product rules and just, all the derivative rules, simple derivative rules in multivariate in basic multivariate calculus. Um, and that's basically it. That's basically it. There's nothing more to even talk about when we're talking about this. However, the more important stuff that we are going to talk about lies beyond the actual multivariate calculus and linear algebra. Instead, we have to focus on some of the basic materials in linear algebra concepts and some of the basic materials in multivariate calculus in order to fully understand the entire picture of state-of-the-art deep learning models, but it's just simply sufficient enough to understand those state-of-the-art learning techniques and even the sufficient and necessary models and learning techniques that you might learn during in your deep learning career uh, without any other multivariate calculus or linear algebra, but simply a very basic understanding of just multivariate or multivariable derivatives and what a matrix is, vectors, what a tensor is, dot products, matrix multiplication, and the Jacobian matrix. Um, was it Jacquard or was it? No, I think it's not Jacquard. Jacobian, yes, the Jacobian matrix for derivatives, and basically that's it. All right, that's as deep as you might want to go to completely sufficiently, almost 99% understand all of the content in deep learning. The most important things that we have to address, though, is the techniques and exactly why. Have a good intuition and have a good idea, have a good picture on why these uh, different techniques that we'll be focusing on works. And in order to understand them, we have to understand in terms of the backward pass, in the perspective of the backward pass. What do the gradients say? What is a gradient? How do we work with the gradient? The backward pass or the gradients are actually the learning material that the neural network accepts. Whereas the forward pass is simply nothing. Its forward passes are just basically nothing in terms of deep learning. Whatever comes out, as long as it's working, as long as the model does its thing, we are fine with it. But for the backward pass, everything that we need to consider for our forward pass to work right, we need to understand the backward pass. We need to understand how do the gradients work and how do we create rich, good, or great quality gradients to the neural network model, right? And that is where we're going to really kind of focus on. And I think most of the things that I'm going to talk about is backward in the perspective of the backward pass instead of the forward pass. So the forward pass is we learn the forward pass to kind of understand how each of the deep learning techniques kind of work. Right? What are the operations that we do? What are the operations that we do to manipulate the data and propagate it towards the finish line, towards the end, right? But once we know that, that's just basically 20% or just basically less than half of what we understand in terms of the significance and the importance of a specific technique. The forward pass does not matter. The backward pass matters. How does this specific operation create even better quality of gradients? How does it create better backward passes? Why does it prevent overfitting? And that's the overall discussion that we're going to have. Now, again, I'm going to kind of write this like great quality, what do you call, gradients. Great quality gradients are information heavy. They're filled with information, but not a specific type of it, not just any information, but about patterns. All right, they're filled with information, filled with content, I would say, right? Filled with content and not just noise, filled with content or signals, patterns, useful patterns, and not noise. right? That's a great quality gradient, okay? And in terms of a bad quality gradient or just garbage, or you can call them as noise, these are the exact opposite. It's filled with noise and just complete random things, uh, and nothing in the context of good signals and good patterns, and you know, inducing a neural network model to converge to a specific pattern. So that is the difference between a a great quality gradient and a garbage gradient. So that is what we're going to kind of focus on. All right, well, let's try it out. Okay, so then let's just focus on how do we get great quality gradients? Because that's what it matters. How do we get great quality gradients? This is where statistics comes in. This is where we could brainstorm and talk about so many different ways to create these great quality gradients. I think one of the other ways to kind of understand how to create a great gradient is to how not to create a garbage gradient. How what are the many ways to avoid creating these garbage gradients? And I think that could be a little bit simpler when we are discussing great quality gradients. Garbage gradients are redundant, or they don't contain a lot of useful information compared to the amount of data that's being fed into. So basically it has very high compression rate, where in terms of compression rate, we're not talking about lossless compression, but lossy compression. What that means is if you're using a lossy compression algorithm to, let's say, for example, let's say we consider a gradient as an information, all right, information content. And it's a file, right? You could consider a gradient as files or information. And you're using this lossy compression algorithm to compress it, all right? You want to compress it. And this is lossy. Then if the information is just completely noise, right, as if it goes noisier and noisier, then the compression algorithm is going to just completely converge to zero. Or it's not going to represent any other type of information. It's just going to be, well, it doesn't matter, right? It's just complete noise. Even if I just generate some random noise, random white noise, like what you see on a TV screen when it's like completely fuzzy, right? Even if I do this random white noise, it is more or less going to be very similar with the noisy compression algorithm. Sorry, not noise compression algorithm, with the noisy data that that has been fed into the information. So if you think of it in terms of that kind of perspective, the lossy compression algorithm is going to produce like complete zero. It's just going to compress the information so fast, right? Because not fast, but like so much, so that there is absolutely no important information content at all. So this is where we're going to kind of take a look into this, where uh, redundancy and the reason why there's so much, the higher the compression rate, uh, the more garbage the gradients are. So let's say you have a information, let's say you have a batch of 16 data points uh, fed into the neural network, but half of them are redundant, so they're the same data points. What would that lead to? That would lead to a very high compression rate. The reason is 8 are completely redundant. We can just simply reduce all of those 8 data points into simply one data point. So that would have a very high compression rate compared to 16 unique data points. Completely unique data points, and they have some kind of a pattern into it. So this is where we're basically working with in terms of compression rates and all that. Now, we expand this idea of a compression rate. Then you might ask, hey, does a completely unique 16, like let's say that their batch is 16, right? So let's say we have a completely unique data points, right? So super unique. They are no different than one another. They are completely different, but they have absolutely no pattern at all. There's absolutely no pattern, right? Maybe it's like when you're talking about a movie, like a crappy movie is like a movie about Jaws and Star Wars uh and I don't know, and The Thing, or and Paddington or Winnie the Pooh, all of those elements in film all just mushed up together, and they just create some kind of a weird fucking film with it. There is no pattern. There is absolutely no pattern. Yes, the movie is the most unique out of all, right? And we might have completely different 16 unique data points, but they won't compress perfect. They won't compress at all. They would just be like water. It would be liquid, right? It won't just simply compress at all, right? Would that be great for a deep neural network? Would that be great for a neural network to learn? Would that be a great gradient? No, not necessarily. That's also garbage, right? If we think about it, that's also completely garbage. So basically, we want to be in the middle of the spectrum. So if this is completely redundant or just completely noisy, right, where just there's nothing to even discuss, and simply a random noise would be similar to these types of data points, we would also have at the end of the spectrum completely unique with absolutely no pattern, with no pattern. And in a way, this is also considered as noise, if you think about it, right? This is also considered as noise. If there is absolutely no pattern, it is irreducible, right? It is irreducible, and worse yet, irreducible patterns cannot generalize out of sample, right? If we're thinking about it in terms of statistics. Irreducible things cannot generalize outside of it, mainly because this means that there is no domain of discourse. There's absolutely no domain of discourse. Or uh but you might argue, oh well, there is a domain of discourse. There is a topic that we are discussing, and there is a problem that has been sampled out of the same environment, out of the same conditions. It's just data that's just completely unique. Then yeah, all right. Then we can agree that there is no common domain. Okay, there's no common domain. There's no common space, you could say. There's no common space where all of these patterns are situated in. There is absolutely no space at all that can encapsulate those data points in some way, and you cannot transform it. It is impossible to transform these data points so that we kind of reduce it, right? There is no form of compression. The only way to do it is to simply memorize all of that data. But data patterns that are completely unique are likely to be the case where if we come up with an out of sample data, where data that has not been trained, or data that is just like we collected in the far future, and there's new data coming in the same domain of discourse, assuming that we do agree that there is a domain of discourse in that case, the out of sample will not match with any of the patterns that the neural network had learned, because the out of sample data points are also going to be completely unique as well, right? They are going to be completely unique. Therefore, there is no predictability, and also there's going to be horrible accuracy and horrible precision in terms of its estimates. It's not going to work out. So we need somewhere in between here. We need somewhere in between here. Is it here? Is it here? Is it here? Where is that, right? And this is now recent. This is a very, very recent and a highly studied topic. And many people call this the 85% rule. Now, I know that 85% seems to be, it has been discussed for a pretty long time, but the actual research the actual research on the 85% rule in machine learning and deep learning, that has that they discussed it in 2020 or 2021-ish. That they discussed it in there. And there's a paper in Nature. They survey, like, not survey, they experimented with so many different mediums of learning agents, and machine learning was one of them. And they figured out, and they mathematically kind of demonstrated that around 85% is good enough. So if we can achieve a compression rate, right? It's a compression rate of 85%. Oh, actually, it's the opposite. Sorry. It should be 85% here. So it's closer to, well, the spectrum is a little bit inaccurate, I would say, in order to plot this in. But let me just explain and try to relate with the spectrum that I kind of made, okay? So the paper says, in order for the machine learning and deep learning algorithm to learn the fastest, they said, to learn the fastest, and that eventually led to more generalization, that led to more, what do you call? That led to more mastery, right? It made the model more robust in terms of its data points. When they trained the model to learn where 85% of the content they already know, right? 85% of content is easy for them, easy for the model. And roughly only about 15% of the content is new. And it's new, they have a high loss, right? They don't know this, it's foreign, you could call them as unique, right? So they haven't seen that before. So if they can simply maintain this balance, right, that learn the fastest. Anything that is beyond that, anything that is beyond these values, seem to, like, equally, the performance deteriorated, and they learned extremely slow. And especially when it came to unique data sets where like 0% of the content was easy, then the model just didn't train at all. And also in the case where 100% or 99% were just completely easy for them, it just the performance kind of tanked, almost tanked as well. So, and eventually led to overfitting. So this is the overall idea. Now, what Nature demonstrated was that this is around a convex problem. This is a very convex problem where simply by changing this content ratio, there is no. I can't say it's convex. I would say it's not necessarily convex, but it's unimodal. Right, there is only one peak, and that's roughly 85%. And they proved it by a variant of maximum likelihood estimation in terms of its own error rates and speed, by using, like, derivatives and all that, and the expected in terms of statistics. But they did demonstrate that this is a unimodal problem, and it followed this what do you call, the logarithmic problem sets, where the overall distribution and the overall training curves, they display this logarithmic type of pattern. But those are most of the things that I kind of talked about in terms of logarithms and all that. That's just, like, straight from my head. I think this is a very interesting topic when we're talking about logarithms, and how logarithms basically nearly very much help deep learning models to converge. And without logarithms, deep learning models are just kind of, they're sitting ducks. They can't do much. So yeah, but that's a story for another time. But anyways, so this is the overall idea in terms of, like, how we situate this in terms of a spectrum. We want 85% of the content to be predictable. We want 85% of the content to be predictable. and we want 15% of the content to be completely new and foreign to a machine learning model. So this is what creates good gradients, all right? So this is where we kind of propose a solution. Now, to recap, we talked about this model of this the ideal lossy compression algorithm. And when we feed the information to a lossy compression algorithm, we don't want the compression algorithm to simply compress every information into some kind of a weird number. But we also don't want the compression algorithm to struggle as well. We want the compression algorithm to be adequately challenged, to compress a lot of the content, almost 85% of the content, mostly into a abstract and generalizable pattern. But for the 15% of the content, the compression algorithm slowly, adapts towards like morphing its own algorithm, morphing its own decision-making process to encapsulate more of the patterns, to encapsulate more onto the 15% of the unknown data that it's been exposed to. So this is the ideal distribution that we need, and this is one segment of how to create good quality gradients. We've talked about in terms of statistical properties as well, right? So to recap, we learned about that seeing in terms of gradients help us have a more intuitive understanding of how deep learning models work. And we have also introduced generating good and bad gradients and what they are, basically. And in order to kind of explain more about these good and bad gradients, we've explained about the signal and noise in information theory to kind of scratch the surface and get our feet wet on how to generate good gradients and avoid generating bad gradients. And in the future videos, we're going to talk about more in depth about how we're generating good and bad gradients and how state-of-the-art models and modern papers that produce state-of-the-art results actually do target in generating these good gradients and bad gradients according to our definition of framework.